Alrighty, hello and welcome back. Today we finish up chapter 4, so this is the last section of chapter 4. Yay! I am super excited about this one. This was a fun one. We'll be breaking it into two parts, but that's okay. But before we get to jump into the fun stuff, we need to do some of the homework. So let's knock out the homework from last time where we were doing let's see, that was section 4.4. And start off with number 9. And for number 9, we had the integral from -1 to 0 of 2x minus 1 dx. Okay? And so this is a definite integral, so the way that we solve that is we take the antiderivative of the function and then plug in the bounds. So this is going to equal, let's see, I'm going to add 1 to the exponent and then divide by that, and then a constant is just x. Like if I have -1 here, what did I differentiate to get -1? I differentiated minus x. So that is the antiderivative. Now I'm going to plug in the bounds -1 to 0. And the way that I do this, I plug the top one in first. So because if this is my a and b, my final answer is f of, oh boy, it's going to be one of those days. f of b minus f of a. There we go. So I'm going to plug this in. This is going to give me 2 times 0 squared over 2 minus 0 minus 2 times -1 squared over 2 minus -1. Okay? So when I do that, I'm going to get, this is going to wind up being 0, 0 minus 0, and I'm going to be subtracting off. This is going to be a positive 1, so it'll be 2 over 2, which is going to be 1, and then this is going to be minus -1, so plus 1. So 0, which is what this whole thing becomes, 0 minus 2 is just -2 for the answer. Alrighty, hopefully that one went well. We can swing on into number 11. Well, we could if I'd assigned that, but I didn't. I assigned 14. That's a 4 down there. So for 14, we have the integral from 1 to 4 of, we have 8x cubed minus x dx. Now, why did I do parentheses on this one and no parentheses on this one? Well, that's because a lot of books will explicitly put what's being integrated inside parentheses, but I tend to not do that because it's obvious. I've got an integral sign here, I've got a dx here, the stuff in between is what I'm integrating. So this is one of those cases where the notation is very unambiguous. You cannot mistake that this is the stuff that you're integrating. So I personally think the parentheses aren't needed. Some people prefer them, so if you do, cool, no harm, no foul. But I won't be using them very often. So here we go. Let's take the antiderivative of 8x cubed minus x. So I'm going to have 8x to the add 1 to that, so to the 4th divided by 4 minus x to the add 1 to that second divided by 2, evaluated from 1 to 4. Okay, so this is going to give me, oh boy, it's going to be a very large number. Alrighty, so let's see, 8x to the 4th. 8x to the 4th, where x is 4. I'll just write it down, then I'll do the actual work down below. So 8 times 4 to the 4th over 4 minus 4 squared over 2 minus, I didn't have enough room here, 8 times 1 to the 4th over 4, and then minus 1 squared over 2. Oh man, we ran out of room. There we go, though. That works okay. What is 8 times 4 to the 4th? Well, first off, I'm going to change that into 2 times 4 to the 4th. Well, 4 to the 4th is 256 times 2 is 512. So this is going to equal 512 minus, this is going to be 16 over 2, so it's going to be an 8. And then minus, this is going to evaluate to 8 over 4, so 2 minus 1/2. Okay, so that's going to be 504 minus 2 minus 1/2 is a 1.5. So this is going to be 502.5 or 502.5, whichever you prefer. Alrighty, hopefully that one went well. Let's move on through. I like these quite a bit. They are fun to be able to plug these values in and evaluate them. So I actually like the antiderivative part the best though. So this is number 15. I sure hope I assigned that one. It's going to be the integral from 1 to 2 of 3 over x squared minus 1 dx. And I am so glad I assigned this one. I cannot take the integral in the form that it's in right now, because I can't just add 1 to the exponent and then divide by that, because it's not outside of the fraction. Right now it's in the denominator of a fraction, so I have no idea how to do this integral. But I can rewrite it. And if I rewrite it, I can do it. So the integral from 1 to 2 of, this is going to be 3 times x to the what? Negative second power minus 1 dx. There we go. Since I've moved it out of the fraction, now it's just a negative exponent. I'm totally fine with that. I can do the power rule, and that should work just fine. So if I do that, I'm going to get, well, let's see, add 1 to, so it's going to be 3x to the, add 1 to negative 2, negative first, divided by negative 1, and then minus, well, the integral of 1 is just x, the antiderivative of that, and then it's going to be evaluated from 1 to 2. So this is going to be 3 times 2. You know what, let me rewrite this to where I can evaluate a little bit easier before I jump in, plug in the values. So this is going to be negative 3 over x minus x evaluated from 1 to 2. It's just going to make it a lot easier to evaluate, to understand what's going on. So this is going to be negative 3 over 2 minus 2, and then minus negative 3 over 1 minus 1. Just like that. Okay, so this is going to give me, let's see, negative 3/2 minus 4/2 is negative 7/2. And this is minus negative 3 minus 1 is negative 4. So really this is negative 7/2 plus 4, and 4 is 8/2, so negative 7/2 plus 8/2, 1/2. Ta-da! Alrighty. And if it doesn't feel natural yet, it'll get better as we go. Alrighty, so for 17, this one's going to be a little bit tricky. We've got the integral of, well, from 1 to 4 of, here we go, u minus 2 over root u du. I have absolutely no idea how to do that integral. I'm going to need to do a couple things to get this into the shape where I can actually work with it. First thing is I'm going to split this into 2 fractions. So this is the integral from 1 to 4 of u over root u minus 2 over root u du. It's already looking better. So now I can work with that because this is integral from 1 to 4 of, well, u divided by root u is just root u. And then this is minus 2. Oh, this is just not going to be pretty any way you slice it. I hate to do it that way. You know what? Let me backtrack so that I can do it consistently. All right. First thing I'm going to do is rewrite this. This is u divided by u to the 1/2. And this is minus 2 over u to the 1/2 du. There we go. I like that a lot better. So that is going to equal the integral from 1 to 4 of u to the first divided by u to the 1/2. It's going to be 1 minus 1/2. It's just going to be u to the 1/2, right? So this is going to be u to the 1/2. And then this is minus 2 times u to the negative 1/2 because the 1/2, the u to the 1/2 was in the denominator, so du. Now that I've got it set up like this, I can use the power rule and figure out what it should be. So let's take the antiderivative. So I'm going to add 1 to this exponent. So this is going to be u to the 3/2 divided by 3/2 minus 2 times u to the, well, it's going to be, I don't know why I wrote it up like that, minus 2 u to the 1/2, because negative 1/2 plus 1 is positive 1/2, divided by 1/2, and that's evaluated from 1 to 4. So this is going to be, when the dust settles, I'm going to have 2/3 u to the 3/2, because when I divide by 3/2, it's the same thing as multiplying by the reciprocal 2/3, and then this is going to be minus 4 u to the 1/2, and that's evaluated from 1 to 4, which you can imagine I've run out of room, but there would be a bar here with a 4 and a 1. Alrighty, so now I can start plugging things in, but before I do that, I'm going to rewrite these u's. Now that I've got them into the right form, I've done all the power rules and adjusted the fractions, everything is the way it's supposed to be. Now I'm going to rewrite them in root form so I can have some sense of what they are. So this is going to be 2/3 times, well, u to the 3/2 is the square root of u cubed, and then minus 4 on the square root of u. So that's what that is, and that's evaluated from 1 to 4, which actually turned out to be not so bad, because this is 2/3 times, well, 4 cubed is 64, the root of that is 8, so 8 minus 4 times square root of 4 is just 2, okay, minus, and I'm going to plug a 1 in, well, that's just going to be a 1, so it's going to be 2/3 minus, that's going to be a 1, 4. And so that's what we get. So this is going to be 16/3 minus, what is that going to be, 24/3? Yeah, so 16/3, I'm going to write it down like this, minus 24/3, and then minus, this is going to be 2/3 minus 12/3. There we go, everything's in thirds. I can work with that. So this is 16 minus 24 is negative 8, and then this is going to be a negative 10, but minus negative 10 is plus 10, so negative 8 plus 10 is going to be 2/3. And that's my final answer. Not too bad. Alrighty, so let's knock out the very last one. If I can clear this. So let's see, 36 was kind of, oh, I forgot, I've got 29, don't I? Yep, got to do 29 first. Don't want to forget that one. 29. I almost skipped it. 29. And that would have been a shame because it's a trig one. So integral from 0 to pi of sine x dx. Oh, I'm sorry, it's actually got another piece, doesn't it? Sine x minus 7. That's a strange one. Why would it have that? Oh, okay. Sine x minus 7 for some reason. Alrighty, so first off, I need the antiderivative. So what do I differentiate to get positive sine x? Negative cosine x. If I take the derivative of negative cosine x, it's negative sine x, which becomes positive sine x. So that's what we want. So the integral of sine, the antiderivative of sine x is negative cosine x, and then minus the integral, the antiderivative of 7 is 7x. Evaluated all this from 0 to pi. Okay, so this becomes negative cosine pi minus 7 pi minus negative cosine 0 minus 7 times 0. Alrighty, so cosine pi, let's think about the unit circle. Pi is right here. What's the x value right there? That is negative 1. So this is going to be negative 1 minus 7 pi, and then minus, what is cosine 0? Cosine 0 is right here, so it's the x value, which is positive 1. So this is minus positive 1 minus 0. Okay? So this becomes 1 minus 7 pi plus 1, which is just going to be 2 minus 7 pi. And the dust settles. All right, not too bad, not too bad. Now, another trig function, 36. Let's do the integral, negative pi over 2 to pi over 2 of 2t plus cosine t dt. Alrighty, what is the antiderivative of 2t? Well, it's 2t to the second divided by 2 plus, what's the antiderivative of cosine t? What did I differentiate to get cosine t? I differentiated sine t. And that's evaluated from negative pi over 2 to pi over 2. Okay, so now I can plug those in. Let's see, I'm going to get 2 times pi squared over 4 over 2. This is strange. But okay. Minus, you know what? I'm going to do it in 2 steps. I don't like how strange that looks. Let me do it in 2 steps. So this is 2 over 2 cancels. This is going to be t squared plus sine t evaluated negative pi over 2 to pi over 2. Yeah, that looks a lot better. So this becomes pi over 2 squared plus sine of pi over 2 minus negative pi over 2 squared plus sine of negative pi over 2. Yeah, that looks a lot better. Okay, so this is going to give me, let's see, pi squared over 4 plus the sine of pi over 2. Well, unit circle time again. Pi over 2 is right here. What's the y value at that location? That is a 1. So plus 1 minus, well, it's going to be pi squared over 4 here as well, isn't it? Pi squared over 4. And then plus sine of negative pi over 2. Negative pi over 2 is going in this direction. So what is the y value there? So that y value is negative 1. So this is going to be plus negative 1. So I'm going to get pi squared over 4 minus pi squared over 4 they're going to cancel. Then we'll have 1 minus -1, which is 2. And that is the answer. So there you go. That's how you work a lot of definite integrals. If it's not singing to you yet, it will. Just practice them. Do a few here, a few there over the next, X months, and okay, maybe not months, weeks, and you'll get nice and solid on it. So no worries at all. Just takes practice. Alrighty, so let me clear this, and then we will move into integrating by substitution, which is a lot of fun. So this is where we get our first look at integration by substitution, like I just said, but I'm not going to call it integration by substitution. I'm going to call it u-substitution. And you'll see why in just a second. All right, so let me show you what it is first. If I have an integral, something like this, maybe x squared plus 1 quantity squared times 2x dx. We've already talked about, I think I mentioned it, I hope I mentioned it, that it's really hard to find the antiderivative of a product. It's not like when you take the derivative and it just kicks in the product rule. A product within an integration is usually very difficult because you have to think, what do I differentiate to give me two things that are multiplied together, which is a very odd thing to think about. So one of the tricks that has been developed to be able to solve products, you'll learn the second trick in Cal 2, but the first trick is when I'm looking at my expression here, is one piece the derivative of another piece? Okay, I'm going to write that out. Is one piece the derivative of the other piece? Okay, what on earth does that mean? Well, looking at this, I can't integrate it in the form that it's in. But what I notice is that this piece right here and this piece right here are related, because if I take the derivative of this piece, I get this piece. The derivative of x squared plus 1 is 2x. So what I'm going to do is make this piece my u, and then I'm going to take the derivative of u. And when I take the derivative of u, I get what's called du. This is a new kind of way to think about things. So it's not going to be u prime or, any of the other notation that we've used in the past. For u substitution, you're going to make your one of your pieces u, and then when you take the derivative of that, you're going to wind up with your du. But what I've written here is a little bit misleading, okay? Because when I fix my u, when I say this is my u, this piece looks like the derivative of this piece, I still write down u equals x squared plus 1, and then I wish I could do it. I wish I could you could see what I'm trying to do in the real world. I cover up this entire derivative. I do not look at it right now, and I figure out what du has to be based solely on what I put in here for my u. So without looking at this, so like put your hand over it. What is the derivative of this? The derivative of x squared is 2x, and the derivative of 1 is 0. So this is the derivative, but do you remember when we were doing the implicit differentiation? When we took the derivative of a function with respect to a different variable, in this case we're taking it with respect to u, the derivative of u, where this is what u is equal to, is going to be 2x dx. Okay? Now, I get that that is not satisfying at all, but there's another way to look at it. Another way to look at it is if I divide both sides by dx, I would get the derivative of u with respect to x is equal to 2x. That is more satisfying to people to see that, because the derivative of u, what is u? Well, u is x squared. So the derivative of this with respect to x is 2x, which is what we have right here. But the calculus way of doing u substitution is I have my u here, I have my x expression over here. I take the derivative of u, I get my du, I take the derivative of the x, I put that derivative in here, dx. So we're going to do this so many times, you're going to get used to it. But this is really the justification for what's going on. It falls out of this one. It doesn't really fall naturally when you just do it this way. But if you think about the derivative of u with respect to x is this. What is u? Well, it's this. What's the derivative of that with respect to x? 2x. This is much more satisfying. So this is the mechanics. This is what's really going on behind the scene. But after you do a few of these, you're going to be totally used to this. Now, here we go. I shouldn't have boxed that in quite so much. I want to erase that because that's going to bug the life out of me. Alrighty, so now I go back to my original expression, and I'm even going to erase this because I don't need it anymore. And I go, okay, u is x squared plus 1, so that's what I'm going to substitute in. It's x squared plus 1, so instead of x squared plus 1 squared, I'm going to get u squared. Okay? Now, 2x dx, I substitute instead of, for that, I substitute du. So 2x dx becomes du. Now, what just happened? By using the substitution process, we went from an x expression dx with respect to x to a u expression du. It is exactly the same the way that it handles. It does not matter, like we saw in the previous homeworks. I could have the integral of, I don't know, 3 smiley, the worst smiley ever, squared d smiley. If I did that, I would have, hello, thank you, I don't need to know about my virus and threat protection. If I did this, it would just be smiley, 3 smiley cubed over 3, which is just going to be smiley cubed plus c. Alrighty, so it doesn't matter what the variable that we're integrating with respect to, as long as they match. As long as they're the same thing, we're good to go. It can be an x, it can be a smiley, it can be a u. So this is the integral of u squared du. What is that? Well, that is u cubed over 3 plus c. Alrighty? But typically, we don't leave it in terms of u. We go back to our x's. U is equal to x squared plus 1. So this becomes x squared plus 1 quantity cubed over 3 plus c. This is my final answer right here. I substituted in u for this. When I did that, it turns out that du took both of these pieces. So I wound up with u squared du. The antiderivative of u squared is u cubed over 3 plus c. Now I substitute back in my x expression for the u. So instead of u cubed, I have x squared plus 1 cubed over 3 plus c. Now, if you want to check your answer, differentiate your answer. See if you get what you have up here. if I differentiate x, well, if I can write x squared plus 1 quantity cubed over 3, well, this is 1/3 x squared plus 1 quantity cubed. So it's going to be, that's a power rule with the chain kicking in, 3 times 1/3 x squared plus 1 to the second power times the derivative of the interior, 2x. So the 3 and the 1/3 cancel. I'm left with x squared plus 1 quantity squared times 2x. Right there. So I did it right. This is the actual answer. You can always take your integration answer, take the derivative of it, and see if you get back your original expression. If you did it right. Guaranteed. So I've just thrown like a ton of stuff at you. So let's do another couple of examples and kind of ease into this. All right, clear this. So let's do the integral of, how about 3x squared minus 5 to the 5th power times 6x dx. Okay? So I'll look at this and go, are any of these two pieces the derivative of the other? Well, yeah. If I take the derivative of 3x squared, I get 6x. So this is going to be my u. So u equals 3x squared minus 5. Du would then be, I do not look at this. I look strictly at this. What is the derivative of this? Well, it's 6x dx. Okay? So now that I've got it set up like this, I can now do my substitution because I have all my pieces. That's my du. So I'll wind up with u to the 5th du. And I can knock that one out in no time. The antiderivative of u to the 5th is u to the 6th over 6 plus c. And now I just substitute back in for my u so I can get it in terms of x. So this is quantity 3x squared minus 5 to the 6th power over 6 plus c. And there you have it. That's the answer. Okay? What if I had the integral of sine x cosine x dx? I can make, both of them are the derivative of the other, but if I don't want to mess with a negative sign, what do I want to make my u? I want to make my u sine x. Because when I make my u sine x, then du, and I do not look at this at all, I look strictly at this. What is the derivative of sine x? Cosine x dx. Okay, now I'll look and see what pieces I can fit in. Well, I can fit in right there. This becomes the integral of u du. That's easy. What is the antiderivative of u? Well, it's u squared divided by 2 plus c. Now substitute in, so this becomes sine x squared over 2 plus c. And there you go. That is how u-substitution works. If one of the pieces is the derivative of the other piece, you can bust out u-substitution. Whew. And now a quick question before I forget, it popped into my head. Why am I putting plus c everywhere, but I didn't on the last set of homework that I did? Right. Definite integrals do not require c. They have limits that tell you where the thing is living, so you don't have to throw an arbitrary constant in. When you do a definite integral, an integral that has an a and a b in it, like that, you don't have to do c. But if it is just an integral that is indefinite, there are no bounds, you have to do plus c. Alrighty? So let me clear this, and I'm going to show you where it gets a little bit tricky. Here we go. Okay, so what if I had this? The integral of 2x squared plus 1 times x dx. Okay? Notice that the derivative of 2x squared plus 1 is 4x, but I do not have a 4, I've got an x here. Okay? But I can put a 4 there if I want, as long as I adjust by a 1/4. In other words, if I put a 4 in and a 1/4, that's 1. I haven't changed anything. I've changed the form, but not the actual values, the relationships. So I'm still going to make my u equal to 2x squared plus 1. Now, what is my du? Don't look at this. If you look at this, you're going to say x dx, and that's not the truth. Look at this. Only differentiate your u. My du is 4x dx. I've got an x that matches, which is good, but I don't have the 4. So what I'm going to do is put a 4 in and a 1/4 in. So I'm going to do something that looks like this. 2x squared plus 1 times 4x times 1/4 dx. And then, because this is just mucking things up, I'm going to move that 1/4 out of the integral and make this 1/4 times the integral of 2x squared plus 1 times 4x dx. And now everything is fine. I've got my u, I've got my du, everything's good to go. So now I can do the substitution. This becomes 1/4 integral of, well, that's u, that's du, so u du. So u du is, we just did that one. That's not bad. So this is going to be 1/4 times, it's going to be u squared over 2 plus c. So this is equal to, now c is a constant, it's arbitrary. 1/4 times c is still c, it's still an arbitrary, it's still a constant, it doesn't change anything. So this is going to be u squared over 8 plus c. I just sent the 1/4 through, and now I'm going to substitute back in my 2x squared plus 1. So this is 2x squared plus 1 over 8 plus c. And there you have it. That's all you have to do. Oh, sorry. Squared. Can't forget that, right? So, and if I wanted to check, I could differentiate it. I'm not going to, because it will work. But that is pretty much how you handle this. If you have the variable is the derivative of the other variable, the constants you can adjust, but it has to be, the variables have to match. One has to be the derivative of the other. X squared, the derivative of that is x. If this weren't an x over here, I'd be out of luck. Sort of. I'll show you a way to get around that next time, but we're just going to say this derivative of this variable must match the other variable. Okay? Let's try that again. Clear this. And let's try the integral of, how about 7x cubed plus 4 to the third power times, let's see, 3x squared dx. We'll start with this one, then I'm going to make it worse. So right off the bat, I can tell that I've got an x cubed here and an x squared here. The derivative of x cubed is x squared. So I can adjust these constants to be whatever I want. I'll just adjust and put the adjustment on the outside of the integral. So I'm going to try that. I'm going to make this my u. So u equals 7x cubed plus 4. What is du then? Du, just looking at this, is 21x squared dx. I have 3x squared, but I need 21x squared to do the substitution for this. So what I'll do, I multiply this by 7 and take a 1/7 on the outside. So this becomes 1/7 the integral of 7x cubed plus 4 quantity cubed times 21x squared dx. I multiplied the 3 with the 7 and then took the 1/7 on the outside. That way it stays the same. So now I can do my u substitution. This is going to equal 1/7 times the integral of, that's going to be u cubed, and this is going to be du. Okay? I can do that integral. That's the antiderivative, so that's 1/7 times, well, this is just going to be u to the 4th over 4 plus c, which is going to be u to the 4th over 28 plus c, and now I can substitute back in my x, and so this becomes 7x cubed plus 4 over 28, oops, almost forgot, to the 4th power, plus c. That's the answer. Not bad, right? I love u substitution. It's so much fun. It's a puzzle. Okay? Now, I have a question for you. I'm going to do a little box right here. Recopy it. The integral of 7x cubed plus 4 to the 3rd times 3x squared dx. So, why did I make my u 7x cubed plus 4 instead of just the 7x cubed? The 7x cubed, the derivative of that is x squared, which is what I needed for my dx. Why did I make my u include that plus 4? Because it makes it much, much, much cleaner to handle if you go ahead and include that plus 4. When you're pulling in your u, when you're making your u, the way that I've always phrased it, and I've heard it phrased to me back when I was taught it, is make your u greedy. If there is a constant being added or subtracted, pull that in, because when you take the derivative, it goes away, but it simplifies what you wind up with when you do your substitution. If I had just done 7x cubed, if I'd made my u equal to 7x cubed, and then du would be 21x squared dx. When I do the substitution now, I wind up with the integral of u plus 4 cubed, and then I've got to do the adjustment. But you can already see I can't do that. I can't do that integral. It's no longer just a simple power rule. It's got this plus 4 tacked on. So that's why it's important to make your u greedy. If you have a u, your variable has a constant that's being added or subtracted to it, pull that into your u. It's going to disappear anyway when you take the derivative with your du. So it just makes your life a lot easier if you're greedy with your u. Alrighty, so let me do another example. Here we go. This one's not going to look right at the beginning, but it's okay. I would like the integral of cosine 5x dx. Not the integral of cosine x, the integral of cosine 5x. And the answer is I can't do it. I do not know what the integral of cosine 5x is. So what do? I use u-substitution to make it simpler. I let my u be 5x. Then that means the du is going to be 5 dx. Okay? If I make my u 5x, this is going to wind up being the integral of cosine u, which I can do. But I need 5 dx. I don't have a 5 here. So what I do is I add the 5 and put the 1/5 on the outside. Now I can do my substitution. This becomes 1/5 integral of cosine u du. Okay? What is the antiderivative of cosine u? Well, that's just sine u, right? Plus c, and I'll put it in there, but it's perfectly fine if you just put it on the outside because it's when you multiply through, it's going to be like that anyways. So this is going to be sine u over 5 plus c, which becomes sine of 5x over 5 plus c. If I take the derivative of this, I get cosine 5x times the derivative of the interior 5. The 5 cancels the over 5, and I'm left with cosine 5x, which is what I started with. So I did it right. All right. Was that one weird? A little bit. Alrighty. Let's try one that's not too bad. It's going to look bad, but it's not. Let's do the integral of 3x squared on the root of, let's see, x cubed plus 1 dx. Okay? Which of these two pieces, 3x squared or x cubed plus 1, is the derivative of the other, looking at the variables only? X squared is the derivative of x cubed. So I'm going to make my u equal to the x cubed plus 1. Now looking just at this, I do not look over there. What is the derivative of x cubed plus 1? Well, that's just 3x squared dx. And what do you know? I've got 3x squared dx right there, and I've got that part, that u, can go right there. So this was going to become, when the dust settles, root u du. And so I'm going to do a rewrite. That's the integral of u to the 1/2 du. I can now do the power rule with my antiderivative. So I'm going to add 1 to it. This is going to become u to the 3/2 divided by 3/2, which is 2/3 u to the 3/2. Oh, and I forgot my plus c. And then I substitute my x in for my u, and I get 2/3 times x cubed plus 1 to the 3/2 power plus c. And there you go. That's all we need. Alrighty. What do you think? Not too bad, hopefully. Yeah, I know. This is some interesting stuff. I could run into several other little examples, but I'm going to save that for the next video if I don't hit you too hard with this. So let's see, which ones do we want to do? Let me look at this book, because I believe I'm going to start on, sorry, I was eating my pencil. I'm going to stop with things that aren't too horrible. Let me make sure that one's okay, that one's fine, that one is fine, that one's fine, and then that one is okay, And I won't put that one on there. Okay, so for homework tonight, try the following. Let's see. We'll put it right up here. Homework. And this is from 4.5. And it is numbers 9, 11, 13, 15, 17, 39, and 41. And let's star 41, 13, and 17. Let's star those. Give this a good try. I know this is new stuff and it's a little bit weird. We're going to do a lot more practice in the next video, and I'll show you some more advanced techniques for u-substitution, but it is absolutely critical that the basics become familiar. And this is one you have to practice just over and over and over until it finally clicks. So start off with these. We're going to do more problems on the next video, and I will have a rather large chunk of homework for that one as well, so you can get lots of practice. So anywho, I think that will wrap it up for today. Hope you enjoyed it. You have a nice, healthy, happy day, and I will see you next time. Bye-bye.